All right, so today we're so far behind the other class. I think we're kind of where we're supposed to be, and they're ahead. So today we're going to do parsing, which is one of my favorite algorithms. It's amazing how powerful it is, but how simple it is to parse. So the input will be some string in some language with some grammar. In this case, it's an expression, and then the output will be a parsing of it. So for example, or the input could be Java code, and the output could be machine code simulating that Java code. You know, that's a compiler. Or right, so here's some. My son and I wrote a compiler from Java into this this machine code, and it all worked pretty well. It only took us 3 evenings. So and when you're writing a compiler, it's funny because you have to keep track of 3 algorithms at the same time. There's the compiler that you're writing, and there's the Java code that you're reading, that you're compiling, and then there's the machine code that you're producing as output. But we're not going to get any that fancy here. We're going to just look at a real simple example where an expression is a sum of terms, and a term is a product of factors, and a factor is either an integer or an expression in brackets. So you can see, well, this whole thing is an expression. Why is the whole thing expression? Well, it's the sum of terms. And why is this thing a term? Well, the whole thing's a term because it's a factor. Why is it a factor? It's because it's an expression in brackets, and so forth. Right? So, there we go. We didn't start on the first page. Did we? No, we did that. I guess we did start on the first. I made new pages. Where did they go? I guess. All right. What? Actually, I remember where they are. They're not here. They were way at the beginning. Remember, right at the beginning, that's where I put them. So that's it. I did make new expression term things, but I put them at the beginning of the slides instead of here. So, you know, what is an expression, right? An expression could be a term plus an expression, and then the expression could be a term, and then the term could be a factor times a term, and the term could be a factor, and the factor could be 0, and this factor could be 1, and that factor could be that term could be a factor, which is also a 1. Everybody kind of remember that? Which yeah.
This process is meant like non-deterministically?
Yes, definitely. And or you can think about it more as a tree, right? Trees are nice. This is called the parsing tree, right? And we're going to be focused on something that's kind of a legal grammar, where it's a sum of a whole bunch of terms as opposed to expression plus term. Right? So that was good. Now let's go back to where we were. All right, so when you're writing a recursive program, the key is that you really very clearly know what your pre and post conditions are. You know what is allowed as input, what is required as output, and the reason it's so important to know is because you need to use it twice. You need to, when yourself are given an input, and you need to know what the required output is, but you also can have an arbitrary number of friends. And each friend, you can give anything that's a legal input as long as it's smaller, and you just, by magic, you get back from your friend the required output. All right, so you have to really, we're going to really have to trust our friends. So let's write a little bit of code. It's an amazingly small amount of code that's going to parse an expression. And what does it do? It's given S is the entire string. We're not going to change S. It's just going to move around and come back again. It's the entire string. And what's new, the input, is the fact that I tells you where we're going to be starting in the string. So for example, there's a string, and I might be indexed here, so we're starting here. And what's returned is you find the longest valid expression that you can find, and you parse it, and you return a parsing of it, and you return the index one past where you've parsed. So in this case, that whole thing will get parsed, and the J will be right past it, right? But if we were to start here, what's the longest expression starting here? Remember, expression is the sum of terms. So that's going to go inside the bracket, right? If we start here, the longest expression is that. If you start here, then there's no expression. Right? Everybody good with this? So get term is the same, except what it returns is, that's my son coming back from Montreal. I thought I turned this down already. My phone is always up when it should be down and down when it should be up. All right. So, actually, I was talking to a friend the other day when she said she phoned me and I didn't hang up on her proper, and she listened to our class for a while. She thought it was great fun. All right, so term, if you start here, what's the longest term, right? Term is a product of factors, right? So the first term is going to be 6 times 8. And if you start here, term is a product of factors, so it'll be those guys, right? If you start here, a term is going to be the 2, right? If this is here, it won't be anything. And then get factor is the same, except it parses a factor, right? So you start here, what's the first factor? 6, right? You start here, the factor is going to be that. You start here, the factor is the 2. You start here, the factor is all of that. Right? Everybody buy that? So, all right. So let me just warn you now. On Monday, I'm going to give you a new assignment, and you're going to have to write code like this yourself. All right? So you can pay attention to how this code is being written. It's pretty straightforward. So suppose, let's work through the code by example. Suppose we're starting here, right? Well, you look up at the rules, and I'm Mr. Get Expression, so no matter what rule it is, it's going to begin with a term. We call this look ahead 1 grammar because all the rules are the same, and they start with term. And so how am I going? What I need is I need to read a term from here, right? And how am I going to do that? Well, it seems natural that we call Mr. Get Term up here, right? And what does he return? And where do we start? We want the term starting at the same place we're starting, and he's going to return a parsing of a term, and that's the term, and that he returns. And then we say, okay, what's next? Well, either we're done or there's a plus. So we look to see right past that term, right? And you'll note here where we're indexing, the J here got returned was the end of the term, right? Not the end of the term, one past the term. So what we're returning, so when we look for the plus, we just look at it right indexed at J. Right? And we see, is it a plus? And yes, it is a plus. Right? So we call get term again. Now, where does the get term begin? it returns, it's one past the plus, right? We're moving past the plus. And in this way, as you actually run this code, it just rips through read once through the thing that you're parsing. It's an extremely fast algorithm. It just moves through. So here we move past the plus, and we get it. We call get term past the plus, and what does it give us? It gives us the next term, and it tells us where that term is over. Right here is the j for the next term, and we ask, is that j a plus? And it is. So we call one past it, and we get the next term. And then we ask, is the thing past it a plus? And it's not, so we're done. Right? And then we have all the pieces that came from our get terms, and we put them together into be a parsing for get expression. And what might that look like? That might look like a parsing like that. Does that make sense? Everybody good with this algorithm? Yeah?
Professor, what's the use of k there? What's the k doing?
You don't actually need a k. You could use the same j as somewhat you do. K is indexing the terms. So here's p is the parsing of the first term, and then parsing of the second term and of the third term and the fourth term. It's sort of indexing however you're storing. This is, I guess, an array of terms, and it's indexing them. For good luck, I indexed the j as well, just so that they all have their unique names. But you could have used the same j as you flew through there. All right, everybody good with that? So get term is the very similar code, right? Say we're starting there, then back in the last one, you'll see you have to return the j. What j do you return yourself? You return the parsing of the whole thing, and the j you return is still indexing one past what you did, so it's the same place as the bracket, right? So when you're writing this code, really the only tricky parts are knowing who to call based on the grammar, and knowing and paying attention to the j, where the j is indexing, right? It's really not very hard code. So then when we get to get term, it's going to be the same sort of thing. We're starting there. We see, okay, what are our rules? All our rules begin with factor. So we call get factor, who returns to us the first factor. And then we look, what's next? Well, it's either times or we're done. So we look to see, is the thing past our first factor? Is it a times? And it is. So we see what we're supposed to do now is call factor. So again, we call get factor, and we're indexing one past the times. So that's where we're starting from. And we call get factor, who gives us another factor. And then we see, is the next thing a times? And it's not. So we stop and we put the various factors we got together into a parsing of our term. Everybody buy this? Then get factor is a little different. Again, it's a look ahead one grammar, in that we look ahead one and we can tell it's either an integer or it's a bracket. Right? The rule is going to start with an integer or bracket, and I guess we've already tokenized it. This 42 has come as one integer. So we look at that one token and we see, what is that token? Oh, it's an integer. There's some program that will tell you it's an integer, and then you say, all right, if it's an integer, then what's my parsing? My parsing is just that integer, right? And what do I return? I return one past where I started, right? My j is the I plus one past, and we're good. Everybody kind of follow that?
Why is it one pass?
Well, because I is indexing the 42, and and that's our whole thing that we're parsing. So what's passed, what we return is the index past our parsing, and the index past our parsing is the times. So that's why it's I plus 1, just to get past our thing of size 1. In fact, it's these little pluses that moves us through the string.
Professor, could you go over the notations again? Like what does, the parentheses P, X, P, J, X, Y, X, P, V, just like revision.
All right, so S is our whole string, and S at I is the 42, and we ask, is this 42 is it an integer? And it is an integer. So what is our parsing? Our first we only have one factor. We didn't have a string of factors, right? Before we had a string of terms. Now we have one factor, and now we know what the whole parsing is. The whole parsing that we're looking for is just that 42, right? Because the rule is the factor is an integer, and so it is our parsing. Our parsing is that 42. And you can see we go to, that's what our parsing looks like, right? Our factor is a 42, right? So this code is somehow building this tree or whatever data structure you have here. Somehow it's dealing with the 42, right? And then we move past the 42, and we return this parsing and the I plus 1, right? And then we say, well, let's look at another case. Suppose we started here, then we say, oh, is where we're starting, is it an integer? And you'll say, oh, no, it's not an integer. So is it an open bracket? Yes, it is an open bracket. That's fantastic. So what we need next is an expression. So we call get expression. And where do we call it? Well, the expression is going to start, it starts past the bracket, right? So the I, as we know, is indexing the bracket. So we call it I plus 1, which is 1 past the bracket. Right? Does that make sense? And what does get expression do? It parses this it parses this thing, right? And it returns a parsing of it. And so now we see, well, what's next in our rule? Our next is a closed bracket. So we see get expression returns what's past the expression, so that we see, is that in fact a closed bracket? And it is a closed bracket. If it wasn't, we would have had an error message. But it is a closed bracket. So what is our parsing? Our parsing is, what is our factor? Our factor is an expression in brackets, right? And where does our factor end? The expression, 1 past the expression was the bracket, and we want to go past the bracket for it to be past the factor. So that's why we add 1 here, right? People buy that?
So are there 2 brackets before 2, or just 1 bracket?
It's probably 1 bracket. I think this looks like a bracket because it's the circle.
Because at the end, the brackets isn't closed.
I think there's not a bracket here either. That's just the circle.
There's 2 brackets there.
Well, we can see. Let's see. Can we? Oh, there. Yeah, it's another bracket that's way down there, hidden by the circle. Everybody kind of buy this? Any questions about it?
So this one's our recursion?
Well, good question. Is it a program that calls itself?
That's what I'm confused with. You mentioned it was supposed to be a recursion.
Right. Right. Well, it's not. It's super recursion, because get expression calls get factor, and get factor calls get expression calls get term, which calls get factor, which calls get expression. So that's why we're calling it recursion, because
Technically, so you can consider it as recursion.
Yeah, I would call it recursion because it's eventually calling itself. Well, the stack will be that will just go to the height of the parse tree. So it depends on how big your string is. All right. Now, I stuck in a little extra things here. Look ahead. One grammar is a rule in which, given any non-terminal, you look at it has a bunch of rules, and given any two of those rules, the first place they differ is in a terminal. So you can look at see they're all the same until you get to a difference in a terminal. So let's see if we have some examples here. So here, see these two rules, where do they differ? They differ in this non-terminal, right? Where do these two rules differ? They differ, well, this one has a W and this one has anything but a W or an X, right? Where do these two rules differ, right? They first differ in the U versus the V. So the advantage of when you're So we can, in fact, I think we have the code up here. Do we have the code? Do we give you code? Oh, I don't give you code. Oh, no. Well, I guess I was lazy and I didn't give you the code. But we can sort of talk about what the code is. How do you parse get A? You call get B, right? And B gives you a parsing of this B. And then you look past the B and you see, is it the next character a U or a V? Right? And if it's a U, you know it's one of these rules. If it's a V, you know one of these rules. And if it's one of these rules, you call get C. And then you check to see, is it a W or an X or something else? And if it's a W, you then call get E. And if it's an X, you call get F. Right? Does that make sense? And there's examples. In fact, this might be the example that's in the course note, in the practice homework assignment. There's an example of this, and it might be this exact example, right?
Well, can you give an example of a grammar that's not the head one?
Yep. So this isn't look ahead 1 because I don't know whether to call Mr. B or Mr. F first. Right? If I want to recurse this A, here A always called B, but now I don't know whether to call B or F. And unless you had some knowledge about B's and F's, if you knew that B always began with a little b or something, and F always began with an F, then you would know which rule to go with, right? You could be look ahead 1, but otherwise we don't know which to call. So here's another kind of funny grammar. This one's easy to parse. So here I have the grammar for it. I guess the other one came right out of the notes, so I guess I didn't stick the rules in. Here, what do? Get A. It's going to first look to see, do I begin with the bracket? And if I begin with the bracket, it's going to call get A again. And get A will return everything here and leave me at the last bracket. And I just check, do I have a closing bracket past it? Right? Does that make sense? Now, that works great, but will the same thing work for this grammar? Yeah, this grammar is going to have a hard time because we don't know where the middle is. Right? We don't know. If this A is beginning with an A, we don't know whether we're getting this A or this A. It just, you can't parse that without knowing where the middle is. Make it non-deterministic? These?
Dichotomy. You take the beginning, you take the end.
Yeah, but then that would be a different, there won't be a look-ahead one grammar. Right? The look-ahead one grammar is reading it as it goes along, and it always knows what to do next. But here you won't know what to do. You have to kind of read ahead to know whether to cut it in half. Right? All right, so you can't find the middle. So this is how would this recursive program work? Get A is going to immediately call get A, and you know that's problematic, right? Because we're going to call it on the same I, and it's going to loop forever, right? So that's another problem, right? Recursives forever. And so here's a parsing, which is we don't know whether to call get B or get D. But unless we know that B begins with a D, and B begins with a B, and D begins with a D, and then you'll know which rule to use, right? You first kind of peer in and see, are we beginning with a B, in which case we call get B and get C. Otherwise, if it's beginning with a D, we call get D and get C. Yeah?
So the code below is just trying to parse what the context-free grammar is saying, right?
Yeah. Yeah, so you see what we're doing is we know A is either going to be this rule or this rule. But if we know that B begins with a B, then we can check, are we beginning with a B? And if we check, then we don't go past the B, but we call get B. Right? Well, down here, look at that. That should be an E. In fact, I have an E there. Okay, let's see if I can remember to fix that typo. If you guys ever see that I don't fix typos, let me know, because I don't always remember. Yes?
Just to confirm, the lowercase b and d's, they have to be terminals, right?
Yeah, these little guys are terminals. And so that you can actually look in and see what's there.
If they were not terminals, then we'd just be saying the same thing over again. We don't know what they are unless they're defined.
Yeah, exactly. Exactly. All right, so here's the example where B and D could both begin with a B, in which case we don't know which rule to call. Right? Not look ahead one, and don't know whether to call get B or get D. All right, so Chomsky, who we've seen his picture a number of times,